In this video, we're going to look at some modeling using some logarithmic and exponential equations. I encourage you to pause the video before each problem and try to work through it as best you can and then compare your work with mine. So in this first problem, Joey, he's collecting pennies. First day he finds one. Every day after he finds twice as many. So what you can think of is on the first day, he finds 2 to the 0th. On the second day, he finds, so this was day 1. Two pennies. On the third day, he finds 4 pennies. And so you can continue this trend on and on and on. It's like a recursive sequence until you get to over 1,000. Or we can look at what day and how it relates to the exponent and think 2 to the x equals 1,000. So how do you solve that? Of course, we would convert that to a logarithm. Log base 2 of 1,000 equals x. We hop onto our calculator. And we pull up our log base 2 of 1,000. And it takes 9.96 or something along those lines, depending on how we're going to interpret that. So we'll talk about that in a second. So x is about 9.96, something or another. So remember, so we'll call this 10 because we're talking about days. We're talking about a discrete value. So we need to call this 10 because we're talking about the number of countable days. So if x is equal to 10, so 2 to the 10th is equal to, what is that number equal to? It is 1,028, of course. Nope, that's wrong. 1,024. 1,024. So what day is that? If it's 2 to the 10th power, what day is that? That will actually be day 11. Or how many days does it take him to find, in a single day? It's on the 11th day. Context is really important, or you could say 10 days from now if today was day 0 or day 1, right? So context is really important when you're answering anything like this. So why don't you go ahead and check out number 2, and we'll come back. Now that you've had a chance to read through and try the problem, let's talk about it. This model here hopefully looks a little bit like your compound interest formula, PERT. Everybody knows that one as. And so essentially, this guy here is your this 0.0138 number is effectively your growth rate. So that's kind of how to interpret that little model. T is equal to the number of years since 1992. So what was the population in 1992? So that is time equals 0. 1992 is 0 years from 1992. So we would have 5.303 e to the blah, 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 blah times 0. So it doesn't really matter. And then what the rest of this is, anything to the 0th power is, of course, 1. So what was the population? 5.303 billion. So what's really important is that when we have things modeled like this, that p-value is essentially your initial value, your starting point. So that's a really important feature to remember. What is the population t based on this model? Well, today, t is equal to how many years since 1992? 28. So why don't we go ahead and plug that in? And rather than writing it, let's just plug it right into our calculator. So 5.303 hit the ABC to get an E. A to the B power here allows you to plug in some values. So now we have 0.013838 times t, which is in this case 28. So 7.812, we'll just say 7.81. 7.81 watts, 7.81 billion, 7.81 billion watts, people. All right, context is really, really important in any word problem. Now we're going to predict the year that the population will eclipse, will arrive over, will be more than 8 billion. So in order to do that, we have to set P equal 8, right? So we want the first year that P is greater than 8. So what we can do is plug in P equals 8, find out what T value gets that, and go from there. So 5.303 e to the 0.01383 t, and now we have to solve for t. So let's use our skills in exponential equations. First, we're going to get it so that it's only an exponent. So let's divide both sides by 5.303. And so what you get is 1.508 equals e to the 0.01383 t. Now that you have a simple exponential equation converted into a log, again, I'm going to always welcome you to pause the video and try it before watching me do it. But basically, you have the natural log of 1.508 equals 0.01383t. And to get t by itself, we will divide by this. And I'm going to trust that you can put this into your calculator properly to get 29.7. Again, we're talking about years, so we're going to go up to 30. And so it would be it would be the year 2021 that, actually, no, I had that right. Don't round up to 30, because at the beginning of the 29th year, it will not have reached 8 billion. By the end of the 29th year, it will have reached 8 billion. So during 2021, it will have reached 8 billion. So again, let's check that out on the calculator. What you want to do, so straight up evaluating it, it's pretty straightforward. The natural log of 1.508, close those parentheses, divided by 0.0138838. That's where I got my 29.7 number. But again, the other alternative is, rather than straight up solving, remember what we talked about in the previous video, we could graph y equals 8. And then we could graph 5.303 times e to the 0.013838x, and we find out where those meet. 29.7. That's so to be 29.7 years from 1992 is when it hits 8 billion. So at the beginning of the 29th year, it has not yet reached 8 billion. By the time it reaches the 30th year, you have gotten over 8 billion. Now that you've had a chance to look at number 3, there's a couple things that you need to recall before we start. Half-life from chemistry is the time it takes. It's a time period where 100% of something degrades to 50% of something. So that's half-life, right? So you need to know some starting value, and over some period of time, it decays into 50% of its original mass. The other thing you'll have to remember is the general exponential growth, exponential decay function, where you have y equals a times b to the x power, where a is the initial, b is the rate, and x is the number of time periods. So with that in mind, we'll set this up to solve. We'll just call it y, right? So the initial amount, how much do we have? Well, it doesn't really matter, because the initial amount in this particular case is 100% of something. We're just starting with something. So rather than making it complicated, let's just use 1 for our initial amount, because we're looking to have a percent at the end. So if we start with 100%, which is 1, we'll go from there. A half-life, the growth rate for a half-life, 50%. So we'll use the decimal 0.5. And now the number of time periods. So every time a given time period passes, you're degrading by 50%. So if we want to know the number of years, we can't just call it x. We have to call it x over 1620. The reason for that is after x equals 1620 years, 1 half-life will have passed. So this will directly solve for the number of years. If you had just put an x up here in the numerator, if you had just put an x up here in the exponent, I said numerator, but I meant exponent, you would solve for the number of half-lives. So you'd have to get a second answer going on there. So let's just solve it just like this. And there's actually not really too much solving here going on, because after 250 years, we can just plug directly into there. So we're just evaluating. There's actually nothing to solve. So let's just put in 0.5 to the 250 over 1620, just evaluating how much is left after those number of years, and we get 0.89 something or another to get about 89.9%. 89. This thing was 8, 9. Those were the next couple of values that I got. Let's again just pull up this calculator. To make sure you're putting it in correctly, I would do 0.5 to the A to B button here. Again, remember to do 250 divided by 1620. And that's where that number came from. All right, let's take a look at these last couple of word problems, modeling problems. This one's a little bit tricky because at first here we have 2 variables. We need to unpack what's happening there. We're going to return to that familiar amount equals PE to the RT to recognize what R and T. Remember that R is the rate, it's some kind of percentage, and then T is the number of time periods. And so we kind of have to solve for each of those in 2 different phases of this problem. So what we start with is this model. We don't know the growth rate, but we do know 2 things. This 150 here is the initial amount. And we know that after 4 hours, it has grown to some level called 200. So we can actually use that to solve for K, solve for the growth rate. So 200 is the amount, with 150 being the initial. I don't know why I wrote an equal sign. The K, the growth rate, is the unknown, and the number of time periods is 4. So this will allow you to solve for that k value. So take a minute, see what you can come up with here. So what are we going to do here now? We're going to take the natural log of each side or convert into a natural log because we have that base e. So the natural log of 4/3 equals 4k. In which case now you'll divide by 4. And so we get k, again pulling up our calculator here. I'll just keep it right here. And so we've got the natural log of 4/3 that extra parenthesis is not necessary, divided by 4 gets us 0.07, let's call that 0.072. So what that means is that the growth rate is about 7.2%. I don't know why I made a colon there. 7.2%. And we'll use that in the next phase of this problem. So let us now look at the second part of this problem is to estimate the time required for the population to double in size. This is a little bit tricky, so let's keep in mind the initial amount is 150. We're not looking for how long it takes to double here. If you were, you'd remember have to start at t equals 4. What we're looking for is keeping in mind that 150 is the initial. How long does it take to reach 300? So with a growth rate of 0.072, how many t time periods does it take to get from 150 to 300? All right, so solve it in the exact same way as we did in the left-hand column. Divide both sides by 150. Notice you're going to get to a 2 here. And now the actual algebra is identical. So the natural log of each side gives you, remember that we took the natural log of each side over here, and the natural log of e to the 4k effectively cancels out. So now we're going to have 0.07t. Divide by both sides by 0.07. Forgot to write the 2's here, so allow me to sneak those in there. And then t in this particular case is 9.6 hours. It would take 9.6 hours for this population to double at this growth rate. Last part here is about radioactive decay. Once again, very similar to number 3, part number 3. So I would like you to try this one before I do it, and I'll debrief with you afterwards. And so here's what I came up with for part 5 about radioactive decay. If we set up the model in a similar fashion to how we set up number 3, X stands for the age in years, of course. So we plug in what we know. Y is the percentage of carbon-14 that remains, in the same way that Y was the percentage that remained of the radioactive radium. So when we're saying how old, it means we're going to have to solve for X based on a percentage. So you plug in 0.22 as the percent. The 1 is irrelevant here. So X is how old? 5730 is the half-life. So remember that fraction X over 5730 is together the number of half-lives. Bell is ringing here. Sorry about that. So when we get that, that'll directly solve this whole fraction is the number of half-lives. So that means that x is the number of years. Okay, if you just had a variable there, it would just be the number of half-lives. So with a little bit of exponential and logarithmic magic, we can take the log base 1/2 of each side to convert it into a logarithm. And then what happens at this stage, this 5730 was bothering the x, so you're multiplying both sides by it. And where do I get this number? Of course, I get it from $5,730 times.
Ms. Gupta, please call extension 2045. Ms. Gupta, please call extension 2045.
Hope everybody got that. If you are Miss Gupta, you should call that extension. So log base 0.5 of 0.22, and that's where I got my 12,516.75 years. Probably way more specific than actual science could figure out, but based on our model, that is the number of years. Let me know if you've got any questions.